collect a blood sample, it looks like a red blood sample like this, right? And this is called a serum separatory tube, or an SST tube. And that stuff at the bottom is basically is designed to clot the blood. And so after 45 minutes or so, the red blood cells and the other cells of your blood will clot. And then we're going to put this into the centrifuge. And when you see this spin, what's going to happen is that the cells that are in the blood are going to go down below this blockage. This thing here is going to move up, and your serum is going to be on top. And then once we get a nice clear serum, we're going to transfer the serum into a little tube like this. And Mary's going to show us, and this is what's going to go stored in the freezer. And this is what actually all the mass spec analysis gets done on. So this is how the blood gets clotted for 45 minutes with a serum separatory tube. And then when it's spun in the centrifuge like this, what happens is the blood cells go to the bottom, this little part, and then you get this nice clear serum. And this clear serum is what we actually collect and do all our blood work on. The samples then will get stored at minus 80 degrees Celsius in things like this. So everyone's serum sample that we're just collecting right now will go into a tube like this, and it gets stored, okay, forever. And then we go back and analyze them. So everyone who gets a Prodrome scan test, we biobank their blood samples. This is this other mass spectrometry lab. So some of this technology will be part of Prodrome Scan 2.0 or 3.0 as it goes forward. So these are called gas chromatograph mass spectrometers. So it has the gas chromatogram here, and what the gas chromatogram does, if you get a zoom into here, so this is a silica column. It's very, very small, and it's 50 meters in length. And so it's a very, very fine silica capillary column. And it has called a solid phase coated on the inside of it. Right? And then when you vaporize a molecule, so when we derivatize metabolites, like we'll take an amino acid like serine, then we derivatize it into a volatile molecule, and it goes through here and it gets injected at about 250 degrees Celsius. It gets evaporated into the gas phase. And when it's in the gas phase, we use helium or hydrogen carrier gas, and that pushes the molecules through this column. And as the molecule goes through the column, it interacts with the solid phase of the capillary. And so some molecules stick, some don't. They kind of go off and on and off and on. And as it goes through the column, molecules that have different characteristics, different hydrophobicity basically, will start separating. So molecules that have, say a large fatty molecule will stick a lot. So it'll come out, it'll take maybe 40 minutes for it to come out. Whereas a small molecule that has less fat on it will go off fast and it'll come off very quickly. So this then separates molecules in time. And so as it goes through the column, then the glass capillary goes into here, and then this has an ionization source. So the mass spectrometry uses sources like electron impacts. There's an actual electron gun in there, like an electron filament, and like a tungsten filament. And so it'll actually emit electrons. Basically, it's oxidative stress. It's the same oxidative stress that happens in your cells, but we just do it here. So it's an electron beam, and the electron beam basically knocks electrons off the molecule and creates an ion, a singlet radical ion, basically. And in order for a molecule to get measured by a mass spectrometer, it has to have a charge. It has to have a positive charge or negative charge. Now this instrument is called an inductively coupled plasma mass spectrometer, and it runs off an electromagnet. And how it works is there's a big RF generator in here. This argon gas comes in an RF coil creates what's called an argon plasma, which simulates basically the plasma of a sun. And in here, you'll create this massive high temperature, run around 10,000 Kelvin. And so our sun is around 5,000 Kelvin. So this is twice the temperature of our sun, basically. And so through this tubing here, this sucks in an extract from your blood. And when it gets exposed to this extremely high temperature plasma, it vaporizes all the molecules into their elemental compositions. And so carbon, hydrogen, so you get your arsenic and calcium and copper. It measures everything from lithium to uranium. And so those different elements have different masses. And so an electromagnet here, so it's like a magnetic sector magnet. And what happens is when a charged molecule enters the magnetic field will bend it. And so the bending of the ion. So if I take a small molecule like sodium, right, and it'll be bent a lot with the magnetic field, whereas a large molecule like uranium will get bent just a little. And then there's the back end has these little slits that will move, and it'll only let certain window through.
Chase.
Yeah, and then so if I want to measure uranium, the slit is set for uranium, then it goes through that slit, and then it hits the detector, which is an electron multiplier detector. So this is extremely high resolution. It's the most high resolution ICP-MS you can buy in the world. They actually use it for bomb making. They use it for identifying different plutonium variants and so on and so forth. You determine whether the purity of molecules, because it allows us to look at the different isotopes of elements. And then this allows us to do full elemental composition of your blood sample. So if you're looking for, iron or any kind of trace metal, heavy metal contamination. Okay, so now for fun. So this is where it all began. And so this will show you how this real invention all worked in the first place. So this is showing it's a pictogram of the ion cyclotron. And so these TPs 1 through 4 stands for turbomolecular pumps. So the front end here is a source, and this is the pressure, which is at 0, which is atmospheric pressure, right? And then it runs to the center part, which is here, and it goes down to 10 to the minus 6. And so this is the pressure, this is the vacuum pressure that those mass specs we just had in the last room run, like the GCMS is a regular quadrupole mass spec, runs at around 10 to the minus 6 torr. Ion cyclotron has two additional turbomolecular pumps to further bring down the vacuum. And we're now down to 10 to the minus 10. So we're now at a vacuum approaching deep space. And so what we want for this type of mass spectrometer, the vacuum tells us how many ambient molecules are in the air. Okay, it's basically sucking molecules out of the air. And any residual molecules creates spreading. It's like Brownian motion. Like it basically, so we want to, the gases in our air, for example, they have a dampening or a dampening quality, right? They'll basically kind of, it's like trying to run through a crowd of people, okay? So you're running along and you get down street in New York, and all of a sudden all these people slow you down because you can't get through the people. That's what's going on here. So each of these peaks represents a unique frequency and a molecule at that frequency. And what it allows us to do then is measure everything in a blood sample simultaneously. And the accuracy of the molecules, like 802.56, we actually measure it to 4 decimal places, or 5 even. As it runs, this is so what the magnet does, it collects a sample, it spins it, and it collects it, and it adds them up. And we use roughly a 2-second cycle. So the time it takes to run a cycle determines our resolution, because the higher the resolution means that the more frequent, the slower or the longer the frequency range is that we use. And so then you can see here at this 1.4, E8, as the samples collect, this should just go up and up and up. And this is the technology that allows us to get all these small molecules, like low intensity molecules. And this is the power of this technology. This is how plasmalogens were discovered as being relationship to disease. And so this is the technology that we can measure to basically measures everything.